Welcome, Calculus BC. This is lesson 4-6, volume to solids, the disk, washer, and cross sections. Let's begin. So, how do you figure out volume of something? Well, let's back this up. If we integrate a line, which is a function, it gives us an area. It's the area under the curve. So, if we integrate an area, it's going to give us a volume. Think of this going from 1 dimension to 2 and 2 dimensions to 3. So the formula for finding a volume of some figure is the integral from a to b of the area, where area is some function. So it's not going to be like some number. It's going to actually be some function we use to figure out area. And that area then gives the area of the representative cross section. So we're going to have to use one of these functions. And here's a list of common cross sections that we actually use for these shapes. A lot of times we're talking about squares or rectangles. Sometimes we talk about semicircles, sometimes we talk about triangles. So we're going to have to use if I talked about triangle cross sections, you're going to be using the formula for triangle, 1/2 base times height. So these are very common ones. Equilateral is kind of like a special version of regular triangles. So what's the key to solving these kind of problems? So we basically have to set these up, then plug them into calculators most of the time. So the first step is you want to figure out what your limits are from A and B. So this is like your lower and upper limits, like if we're talking like the leftmost x value to the rightmost x value. Boom, boom. You want to know what shape the cross sections are, and then the formula for the area of that shape. So if it says triangles, use triangles. And so make sure you're using that formula. And the tricky thing is in that formula, you got to figure out what represents the variables. Like the area of a square is like side squared. Well, what is side? It's not. Is it a number? It's usually like one of the functions that's involved in there. Sometimes these are constants, but usually it's going to be some function or maybe some version of a function because it's changing. If you notice one of the sides is changing, it's going to be related to a function. So let's do some examples and show you what that means. So first, we're going to watch some animated GIFs or GIFs of what's going on. This one on the left is doing cross sections that are squares, and you notice start off with this triangle shape, but it's building a bunch of squares. This one's building triangles, and this one's building half circles, semicircles. And just watch it and be amazed. All right, so we're going to take this example. We'll go through the rest of the class, but I just want to look at this left one right here. What would be a formula for this? Let's make up some numbers from this. Let's say this is going from 0. Let's say this is 5. And this top line represents some function f of x, and this bottom line represents some function g of x. They're linear functions, but whatever. We don't care what they are. I'll just say f and g. And this is just kind of our limit right here. How do I come up with an integration of the area? So remember, I have to talk. The first step was check out your limits a and b. Wow, that restarted those. So my leftmost, let's say it's 0 in this case, and rightmost would be 5. And we're forming squares, and the area of the square is side squared. So what's the length of one of these sides? So it's like one of the sides right here. And notice the length is from like the lower portion here to an upper portion here, and it's a straight line. And this changes as you go around. Like if I try to draw these squares, like as a really bad 3D drawing, there you go. These squares are getting bigger. So I know the distance is this length, but how do we represent it? Well, it's basically like the point on this function, f of x, to the point on the g of x function. The length between two spots would actually be the difference between those spots. So what I can say, my area, instead of saying side squared, side is going to be the difference, f of x minus g of x. So I'm going to integrate from 0 to 5 of f of x minus g of x squared. dx, whatever function those are. I plug that in, I get my area. And that's because we're doing squares. Now, if I did semicircles, I'd have to do a different formula. All right? So we can talk about more of that in class. Let's take this problem. So find the volume of the solid whose base is a triangle, and whose base is a triangle bounded by this line. This is the y equals negative 2x plus 2, x equals 0, which is this line, and y equals 0 is this line. So basically, you're trying to find this area right in here. And it's forming a triangle shape. It says whose cross-section are squares. So again, we're going to do the side squared thing. Again, we're talking area. And are perpendicular to the x-axis. That's important because how do I know if the squares aren't like coming out this way or if they're growing out this way. When I say perpendicular to x-axis, that means they're going to be up and down. So it's like squares that are popping out like this, going down. That means the length of the side is this distance right here, like that terrible square drawing I just did. The length of one side is this distance right here. What is that distance? Well, notice it's changing, so we know it's going to be some function. And it's going to be relative. This is really our only function with a variable that's changing. So it's going to be relative to this. And in fact, the length of side in this case is going to be just negative 2x plus 2. Because the length of that side is just whatever x is at that point. And plugging into this negative 2x plus 2 equation. So setting up the volume, and notice I go from 0 to 1. And that's what this example said. My side is negative 2x plus 2. So the actual answer is from 0 to 1 of negative 2x plus 2 squared dx. All right, so we got to find the volume. Now I could expand that and integrate, but let's do it on a calculator too. So I'm going to use my, not that one. I'm going to use fn int. I'm going to, or n int right here. I'm going to integrate. My function is going to be negative 2x plus 2 squared, and x is my variable from 0 to 1, and what do I get? I get 1.333. So my answer is 1.333, which is the same thing as 1 1/3 or 4/3. Any answer would have been okay. All right, let's move on to something else. So we'll do that later. Disk formula. All right. So think about disk formula. This is like doing another shape here. Disks are basically circles. So the area of a circle is pi r squared, and that's where the disk formula is, pi r squared. We put pi on the outside because it's a constant. It doesn't need to be inside the integration. Could put it inside, but it doesn't matter. So the volume, when you're talking disk formula, and we're talking about revolving a disk, like you have this linear function right here, and you revolve it around the x-axis, you form this kind of shape. It's called the disk method because it's a bunch of disks. And your radius is basically the length from your axis of revolution to up to where your function line is here. And these are very common in the AP calculus test. So there's the formula. Now let's set up an integral. So this is what a typical problem would be like. So we're going to set up an integral for the volume of a solid formed by revolving the region bounded by y equals x squared, which is this function, y equals 0, which is this line right here, and x equals 1 about the x-axis. So it's basically this shaded area. It's going to revolve like this and kind of have a 3D representation right there. But when it revolves, it's going to do this shape. You're going to have, it's going to form this like cone that kind of just like spreads out. So what would that integral look like? Well, you know that the volume is going to be pi, an integral from what to what of r squared dx. Well, so the integral is going to go from 0 to 1, because that's my left to rightmost y values, or x values. And what's the radius going to be? Well, looking at this picture, it's the radius is the length from the axis of revolution up to the graph. So my radius is just going to be x squared. So I can say the volume is pi, integral from 0 to 1, of x squared dx. So x to the 4th. And I could set that up and evaluate it, but you guys get the point. Let's do something a little bit more interesting. Okay, washer formula. So it's very similar. Washer is basically a circle within a circle. There's a hole in here. So we have an outside radius, so this is the revolution. We have an outside radius, r, and then we have an inside radius, little r. So the volume, the formula is pi times the integral from a to b of big R squared minus little r squared, where big R is your outer and then little r is your inner. So it's outer minus inner. And dx dy just it depends on if you're revolving on which axis. So here's some examples of this. And I'm going to do like 2 of them. We'll save the last one for class. So we're going to set up integrals for each of these cases. So we're going to revolve this one. This is like the disk method of what we just did. We're going to revolve this about the x-axis. So what happens when it revolves around the x-axis? It forms this kind of football shape. You can kind of see it. So let's see. I know my function here is negative x squared plus x and y equals 0. It means it's revolving around this. And it's revolving around the x-axis, so I'm going to say it's going to go from 0 to 1. and the function's negative x squared plus x squared dx, and don't forget the times pi. So there's my setup for the volume. Pretty simple, plug it into a calculator. Now this one's different. So notice my radius, it's revolving it around the y equals -1. When I revolve the shape around -1 here, I'm going to have this big gap. So it's actually, like the inner radius is going to form, this is like the inner radius here. It's actually going to go down. Think of this as the inner radius. This is going to be like a white space right here. Then this little like half circle thingy, it's actually going to revolve way out here. And so like the outer radius is going to do that. So we have this like big gap right here. And that's going to be important when we try to figure out our equations for big R and little r. So what is the radius of each of these things? So let's do little r first. What's the length of little r? And notice the length from the axis to wherever little r is, or wherever it kind of cuts off. Since it's about y equals -1, notice the length of this gap here is always -1. So our radius for little r is, it's always 1, because -1 to the x-axis right here. So my radius is going to be 1 for little r. Now, for the big R radius, this is where it gets tricky. Since we're revolving around -1, think of this as this kind of got bumped up like 1. This, like, it's not, I can't just say big R is this function squared, or this function right here, because this got bumped up. So I'm actually going to say it's -x squared plus x plus 1, because there's this extra gap right here. So when I write those formulas out, it's the integral from 0 to 1, and from 1 times that pi of big R squared, so it'll be -x squared plus x plus 1 squared minus 1 squared dx. So that's how you set up that one. And we'll do this one in class later. All right, that's it for examples.